Hello, and welcome to this next lecture in learning and performing new skills. This is part of my series in cognitive neuroscience. This is part of our module in motor learning and action learning. So what we're going to be talking about today is a little bit about how we learn and perform new skills, particularly motor skills. It's a bit of a prelude to the next series of lectures, which will all be in the cognitive neuroscience of memory. What we do is we're going to start off by talking about how we have a shift in cortical control with learning and talk a little bit about what that looks like. We'll then look at neural mechanisms of adaptation, talk about expertise. I'll introduce you to a model of learning and adaptation and the cortical structures involved. And then finally, I want to talk a little bit about observational learning and mirror neurons and how that's related to motor learning. So the first thing I want to talk about in terms of shifting in cortical control with learning is kind of how the cortex shifts control as we start to get things more automatic. And I want to introduce you to how those cortical skills develop. Start by talking about the myth of muscle memory. I'm going to introduce you to the concept of implicit memory, which we'll be spending some time on, and then get into discussing building new skills and how those motor skills get put together. But let's start with the myth of muscle memory. So we all hear about this idea about developing muscle memory. Athletes talk about it, coaches talk about it, the military talks about it. Basically what they're really talking about is developing new motor skill. Not anything that's tied to a muscle, but a particular motor plan or sequence of motor events. And what's important to understand about most of our motor skills is they're not linked to a specific effector system. That is, they're not tied to specific muscle groups. They're actually a cortically represented motor plan. So in this particular example, this person has written the same phrase, cognitive neuroscience, using their dominant right hand and then their right wrist, and then the left hand, and then their teeth, and then their feet. While obviously their handwriting gets worse as we go down the line, you can see that they're relatively similar. That is, these look like they were all written by the same person in various states of ability. What that indicates is those motor plans aren't tied to the muscles, they're tied to the brain. And that's one of the things we have to keep in mind, is that there really is no such thing as muscle memory. What we mean is the development of an automatic motor plan, or what we call automaticity. And this is one of the things law enforcement agencies, so if you watch any of the specials on how the Secret Service trains, for example, one of the things they want is they want people to react. They don't want them to think. They want them to execute a pre-planned series of motor sequences. And they are timed right down to who's going to do exactly what. You know, if there's a threat to the president or another protectee's life, one person's job is simply to make themselves as large as possible to get between the potential threat and the protectee. Somebody else is going to shove the protectee into the car. Somebody else is going to try to there are just all these sequences of events that happen automatically. And so that automaticity is something we discussed under attention, but that development of automatic behaviors is part of what we're talking about with this development of motor skills. So that gets us into talking about implicit memories. And implicit memories are memories that lack really conscious awareness. We're not consciously always activating them, or we don't have conscious access to the memory. And there are a number of different kinds of implicit memories, or what Larry Squire calls non-declarative memories. So these include things like skills. So your ability to ride a bicycle, for example, is a great example of an implicit memory, that you get on a bike and you ride it. You don't consciously retrieve information about how to ride a bike. And in fact, if you did, the entire time you were riding, you probably would fall over. Because that ability to balance and ride and do all the other things that are involved in riding a bicycle are automatic. And if you try to exert conscious control, your conscious control is going to be much slower, and it's not probably going to go very well. In the memory literature, and we'll talk more about this in the coming units, we talk about what's called recollection versus familiarity. And in these two types of memory, they are types of episodic memories. And recollection are memories for which we have clear conscious awareness. These are linked to particular times and places, or what we call context-dependent memory. We'll also often refer to them as hippocampally dependent memory. Familiarity is where we identify a memory but can't consciously access its information. So the easiest example of recollection versus familiarity is, say you were walking down the street and you see somebody and you say, "That's Bob, he's in my cognitive neuroscience class." That would be a recollection because you cannot correctly identify the memory with time and place. Versus walking down the street, seeing somebody and saying, "That person looks really familiar, but I can't identify, I don't know where I know them from. I don't know who that is." That's a familiarity response. That is, you have identified that there's a memory, but you can't consciously access the memory itself. So that's a kind of episodic implicit memory. We'll also talk a little bit about classical and operant conditioning. Classical conditioning, of course, occurs very rapidly. In humans, the easiest example of classical conditioning is what we call eye blink conditioning. When you puff air into somebody's eye, they will blink, and you can actually then classically condition that to the ringing of a bell, just like any other kind of classically conditioned response. Operant conditioning is something we'll get into later on when we get into motivated behaviors in a couple of chapters. So we're going to get into more of this later, but we kind of have to have some introduction to this idea of memories that don't have conscious awareness. So our motor system has basic movement patterns that are controlled by subcortical circuits. And so when we want to build a new skill, we take things we already know how to do, and then we adapt those. So basically, learning new skills involves building on those basic patterns or linking together a series of movements in a novel way. And so if you're trying to learn how to pitch fast-pitch softball versus slow-pitch softball, you probably have some of those motor sequences down. You just need to adapt them. Similarly, if you're going to go from kickball to bowling, similar motor plans and motor sequences, but they're going to have to be adapted because they're very different types of motor sequences. In my life, I started out in the nightclub business in the early 90s, in fact, 1990. As a bartender and a DJ, and I learned how to DJ using SL1200 Techniques turntables, and basically spent most of my career using vinyl records, which you can kind of see here at the top. It's the basic idea of a vinyl record setup. Well, in this day and age, some nice things. I don't have to haul crates of records around anymore. In fact, I just last year sold off my entire record collection and have gone entirely digital. I have a similar control panel to what you see here. Mine's not nearly that sophisticated because I have a $200 mixing board versus this $1,300 one you're looking at. Anyway, similar basic concept. And so essentially what I've had to do is I've learned to adapt to digital technology is I do the same. The mixing's all the same. The music's the same. I do basically everything the same. I just had to go from using a full 12-inch vinyl disc to speed up the music, slow down the music. I also had to adapt a little bit, not to get too technical, but when I'm DJ with vinyl slowing down a record, oftentimes they'll just put their finger along the platter that's spinning to just slow it down a smidge, or we'll take that record and speed it up a little bit by pushing it forward. And in this new digital technology, essentially you have to wind these dials backwards and forwards, but they respond very well, and the technology actually has come a really long way. So it really is very similar. So the skills did transfer, it just required some new learning. Related to learning is this question of adaptation. And so we're going to kind of delineate sensory motor adaptation from sensory motor learning. What I was just describing was sensory motor learning. But we want to talk a little bit about sensory motor adaptation. So it's a form of motor learning in which a learned skill is modified in response to a change in the environment of the person. And there are a number of examples of these we're going to talk about in a moment. So there are things like using prism goggles to shift a person's perspective 90 degrees to the right or even completely upside down. All of these are potential ways in which you can alter the perceptual environment. And what happens is the people we're actually very capable of adapting. Our brains are quite plastic, and we can adapt to that alteration in our environment or the way we perceive our environment. Other examples include, if you were walking, into a really stiff wind for a while, and then you turn the corner and you might stumble a little because your motor system is adapted to trying to push harder against that wind. And then we're going to talk about sea legs too here in just a moment. So learning occurs when the motor system learns from a sensory prediction error. And in fact, you can look on Google, and for my class I will post some of these videos. There's some really great videos, for example, of people learning to shoot basketball with these prism goggles where their perception has been shifted in about 45 degrees to one direction or the other. The other thing to realize about this adaptation, while it happens fairly quickly, you also have to go through a de-adaptation period. That is, you don't instantly return to normal. You have to actually sort of de-adapt and go back to dealing with normal. So in the prism video examples that you'll see, basketball players learn to shoot with the prism goggles on, and then when they take them off, they're inaccurate again because now they're shooting basketball based on the belief that the basketball hoop is somewhere where it's no longer, or basically because their perception has changed back to where it's accurate, I should say. So that period of de-adaptation does take some time. So some examples of this kind of adaptation are these kind of prism goggles. This is somebody who has prism goggles on, who was out riding a motorcycle, which I find slightly odd, but it was a photograph I found. Mirror tracing is another great example of this, and we're going to talk about this with patient HM, which is the data you see here, in which what happens is you can't see your hand, you can only see a mirror reflection of your hand, and you learn to trace around objects with this kind of apparatus by looking in the mirror. One of the things you might have noticed, those of you who are doing lots of Zoom classes, your Zoom feed on your computer of you is actually a mirror image, and everyone else is not. I discovered this because I had a virtual background I was using that on my computer was backwards, but on everyone else's computer it was not backwards. And the reason we do that is because they don't want you to have to adapt to not looking in a mirror. That is, when we're used to seeing our own face, we're used to seeing it in a mirror. And your front-facing camera does the same thing as well. So anyway, that's mirror tracing. And then finally, sea legs. Any of you who might have spent any time out on the water, particularly if you're on a smaller boat and out in the ocean, or if the ocean's a little bit rough, your motor system adapts relatively quickly. That is, you can keep yourself upright, you can stay pretty steady. What happens, though, is when you come back to land is you have a really hard time walking because your motor system is so used to dealing with that imbalance that it becomes more difficult. And we see the same thing. You can see people at airports trying to get off of the moving walkways. They've very quickly adapted to that movement, and then all of a sudden they're going slower and they have to kind of figure that out. So all of these are adaptation and de-adaptation. So that gets us to actual sensory motor learning. The cortical areas involved in sensory motor learning really depend on the type of learning, and we're going to talk more about this in a minute when we talk about the model I want to discuss. So for example, if we use a visual perturbation such as the prism goggles, it will actually increase visual cortex activity in addition to, of course, the motor cortex activities. But for most of these, we see increased activities in prefrontal, premotor, motor cortex, as well as cerebellum and basal ganglia areas. And we'll get into some specifics about this with both adaptation and sensory learning. I want to spend a minute talking about development of expertise. Going from a student driver to an experienced driver, being an expert sniper or an expert athlete and Olympic champion. All of these are developments of different various kinds of expertise. So we go from being somebody who knows nothing about what we're doing to the development of some sort of expertise. So there are some issues in terms of how we go about developing expertise. And the first part of this is it does oftentimes require some kind of innate ability. That is, not everyone can be an expert in any given field. I am never going to be a professional basketball player. One, I am clumsy as all get out, as we already know. The fact that I tripped and knocked a 2-foot candle on my head and got a head injury a couple weeks ago. But I'm also only 5'8", or just under 5'8". And I was never going to be a pro basketball player. I don't have that ability because I don't have the athletic body for that. So basketball, other sports require an athletic ability that not everyone has the innate ability for. There are certainly certain genotypes that do, better able to develop muscle. In fact, in your 23andMe or Ancestry DNA types, you will actually get some assessment of athletic ability. And in my family, I haven't had mine done. My brother has. But my sister, my brother, and I all can develop muscle very quickly. I have terrible cardiovascular fitness, but I can put on muscle very quickly. And it has nothing to do with anything other than genes. And so there are certain parts of this that are genotypical. There are also some sex differences in some abilities. And so that's one of the other things we have to keep in mind is not everyone, this isn't always an equal playing field. Men have larger muscles, develop muscle more quickly, and have larger lung capacity. And so athletics, men will almost always have somewhat of a physical advantage. Now, that doesn't mean there aren't terrific female athletes. There are many, many more women who are better athletes than I am. I don't even want to think about that as a question. My sister's an incredible athlete. I am not. But men can develop muscle faster and easier because of increases in testosterone levels. We also tend to have larger rib cages and larger lung capacity. Women are better at making fine motor movements. There is some evidence that this is associated with finger size, that if you adjust for finger size, length and width, you lose some of these sex differences, but they certainly are oftentimes better at very fine motor movements. And in fact, women actually make the best snipers. Women are better at shooting guns than men are because of that fine motor movement ability. Also very good at other fine motor sequences, things like if you've ever had to have a crown made, women are particularly good and very skilled at that. Practice is, of course, another issue associated with expertise. There's always these, 10,000 hours will make you an expert. Well, and you'll get probably as good as you're ever going to get. Depending on the kind of practice, though, and that's really important. So many hours of practice are certainly required. If you want to learn how to play the piano or the violin with a level of expertise associated with, say, a member of a symphony, it's going to require thousands of hours of practice. But much more important than just those hours of practice is the kind of practice you do, and we call this deliberative practice. And the same holds for your studying. When you study for an exam, you want to be deliberative. And you want to be expanding your skills, you want to be pushing yourself. And in fact, a lot of people who are experts in the field really dislike what they do because practice is so difficult and onerous because they're constantly having to make it harder, make it more difficult, stretch, push harder, do more. And so that's really important when we talk about deliberative practice, and there's some really good evidence for that. The other thing that's really important is how you practice. And in fact, we recommend for pretty much any kind of skill acquisition or memory acquisition what we call interleaved practice. And that is you switch up what you're doing all the time. So rather than practicing the same music piece over and over for 30 minutes and then practicing another music piece for 30 minutes, you should play one piece and then play another one and then play a different one. And then go back to the second one, and then go back to the first one, and go to the third one, and mix it up. And while that sounds like a horrible idea, it actually results in much, much better long-term learning and skill acquisition. And there is a great deal of research on this for musical ability, for your ability to hit a baseball, for being able to score in badminton. I mean, the number of studies on interleaved skill acquisition is very great. So if you want to try this out, if there's something you're trying to learn how to do. I'm a dart player, at least I kind of was until, you couldn't go to bars anymore. Putting up a dartboard in the back. But one of the things we often make the mistake of doing in practicing for darts is throwing at the same number, say the triple 20 all the time, or bullseyes all the time. It's a terrible way to go about it. You really want to do test yourself and go all over the board, try to hit 3, then try to hit a 20, then try to hit the bullseye, and really kind of mix it up because you'll get much better at that kind of motor skill. All right, that gets us to a model of learning and adaptation. This is a revised model. It's a little bit hard. I did not create this figure, so don't yell at me. But it's a little hard to see with the gray, particularly for somebody of my age. But the way this figure works, and there's a larger figure we're going to take a look at in a minute, is the gray structures you see in that sort of first large box are structures that are involved in both motor sequence learning and motor adaptation. So we're both learning new skills or adapting to, say, prism shifts or something like that. So if you see here, we have the medial temporal lobe, in particular the hippocampus, cerebral cortices and nuclei, or cerebellar, sorry. So lots of involvement of the cerebellum, which we talked about in previous lectures, and the parietal lobe. We also have motor cortical regions, sensory motor areas, the association striatum and the striatum. All of these are involved in both motor sequence learning and motor adaptation. So early on, adaptation and learning use similar brain regions: frontal, parietal, cerebellum, and striatum. These are also the critical areas. Motor adaptation moves to a cortical cerebellar circuit as it becomes more automatic. So as you're no longer having to consciously think about how to hit the basketball hoop with those shifted prism goggles on, and it becomes more automatic, it's going to shift from involving all of these areas to a cortical cerebellar circuit. For a skill, for a new motor learning sequence, so you're trying to learn a new guitar riff or learn how to do knitting or whatever it is you're trying to learn, once that's become automatic, we have then reliance on a corticostriatal circuit. So if we look at this model in full, you can see that the bluish kind of purplish color, these are the motor sequence learning. So we now go consolidate out to the striatum, and as we become more automatic, we're in motor cortical regions, parietal cortices, and the striatum. And then after we've learned them well, and we come back to retain them and see how well we've retained them, it's those same regions, motor cortical regions, parietal cortices, and the striatum. For motor adaptation, now we're looking at more like cerebellum, parietal cortices, and the motor cortex. So it's a cortical cerebellum for motor adaptation and corticostriatal for motor learning. The final point I want to talk about is observational learning, because this is a very interesting part of thinking about how we learn new skills. You actually can learn quite a bit by watching somebody else perform a skill. So observing someone perform a motor skill you're trying to learn engages those same neural systems as when you engage in the motor skill. Studies show that observational motor learning can improve action, perception, and motor execution. So watching somebody do something can actually improve your execution of that same sequence. Moreover, action, perception, and action execution interact in a mutual and bidirectional fashion. That is, visual-motor and motor-visual interactions occur in both directions, suggesting that perception and action share common neural mechanisms. And finally, it's mirror neurons. And so mirror neurons are an important part of what we're going to be talking about when we get to emotion in particular, because our ability to understand facial expressions probably relies on mirror neurons as well. And for those of you who are not familiar with the concept of a mirror neuron, it's basically a single neuron that engages a motor sequence and perceives that motor sequence. So for example, you would think about a group of neurons processing a facial expression like a smile. Those same neurons would be involved in creating a smile. And this is how we're able to infer the emotions of others, because they involve the same emotional states. And so these perceptual motor improvements induced by observational motor learning appear to rely on motor neurons. All right, that's a quick introduction to motor learning. We're going to get into memory in lots of detail in the next set of lectures.